it's usually considered to have given rise to the idea of emergence in physics. Anderson went on to win a Nobel Prize. Since 1972, many other examples of emergence in this technical sense have been recognised. One striking case is that of sound quantization. As everybody knows, sound consists in a wave motion through the molecules of a medium, such as the air. The molecules of the medium vibrate, each passing its vibrations on to the next. It turns out, however, that under certain circumstances, sound no longer consists of a wave, but of particles. The physicist Robert Laughlin, co-winner of the Nobel Prize in Physics, describes it in this way. This is from his book, A Different Universe, page 106. This astonishing phenomenon of sound quantization is the closest thing to real magic I know. Sound is familiar to everyone as the vibration of elastic matter, typically air, but also solid walls, as you know if you've attempted to sleep with a loud party going on next door. Of the two, sound in solid is the more interesting from a quantum perspective, because it continues to exist and make sense even at ultra-low temperatures. Measurements at such temperatures reveal that it is particulate, that is, it consists of particles. Suppose, for example, a sound transducer is attached to a solid and turned on, thus beaming sound into the solid. And suppose that it is then reduced in intensity to make the amount of sound small. A sound receiver on the other side of the solid detects not a faint tone, but sharp pulses of energy arriving at random times. This quantized transmission of pulses evolves into the more familiar transmission of tone when the intensity is increased. An everyday example of the emergence of Newtonian reality out of quantum mechanics. The conclusion, he says, becomes inescapable, that particles of sound exist, even though they don't exist when the solid is disassembled into atoms. The particles emerge, just as the solid itself does. In another portion of the book, he argues that solids are emergent forms, emergent phases of matter. Sound quantization is a particularly instructive example of particle emergence, he says, because it can be worked out exactly in all its detail, starting from the underlying laws of quantum mechanics obeyed by atoms. The analysis also reveals that the particles of sound acquire more and more integrity as the corresponding tone is lowered in pitch and become exact in the limit of low tone. Very high-pitched sound quanta propagating through a solid can decay probabilistically into two or more quanta of sound with a lower pitch, this decay being aptly analogous to that of a radioactive nucleus or an elementary particle such as a pion. The quantum properties of sound, he says, are identical to those of light. This fact is important, for it's not at all obvious, given that sound is a collective motion of elastic matter, while light ostensibly is not. If the theory of emergence is true, it constitutes a profound revolution in our way of seeing both the world and science. A revolution which seems perhaps as important as the discovery of quantum mechanics. It implies that no particular level of reality is epistemologically privileged. The micro level is not more fundamental than the macro, nor the macro than the micro. But both are of equal importance for understanding the universe. Many of the collective phenomena, namely those that emerge, are not necessarily caused by the single phenomena out of which they appear to be built, but each must be understood in the light of the other. In other words, all levels of reality are equally real and equally significant. Lachlan sums the situation up in these words. What we are seeing is a transformation of worldview in which the objective of understanding nature by breaking it down into ever smaller parts is supplanted by the objective of understanding how nature organises itself. In other words, the theory of emergence is not reductionistic. He goes on to argue that the implications of emergence theory are so far-reaching that they effectively usher in a new scientific era. Much as I dislike the idea of ages, he says, I think a good case can be made that science has now moved from the age of reductionism to an age of emergence, a time when the search for ultimate causes of things shifts from the behaviour of parts to the behaviour of the collective. Lachlan refers to a number of scientists who believe that science has gone as far as it can and now has no future. In his view, however, we live not at the end of discovery, but at the end of reductionism, a time in which the false ideology of human mastery of all things through microscopics is being swept away by events and reasons. This is not to say that microscopic law is wrong or has no purpose, but only that it's rendered irrelevant in many circumstances by its children and its children's children, the higher organisational laws of the world. Lachlan gives many other examples of emergence, or what he believes to be emergence. In truth, he extends the range of the concept and the theory well beyond what is generally accepted at the present time in the scientific community, if I am not mistaken. The fact is that emergence theory is admittedly in its infancy and is still highly controversial. The basic concepts in it are not entirely clear, not even the line of demarcation between what emerges and what does not emerge. The term emergence is used widely outside of the scientific context in many different senses. This has led some writers to draw a distinction between weak emergence, as when we say, for example, of somebody that he emerged from hiding and gave himself up to the police, where there is no new substance or law involved, and strong emergence, where there is a new substance or law or something of similar magnitude involved. So some such distinction is certainly needed. If, however, the theory of emergence proves to be well grounded, as indeed it appears to be, at least to some extent at the present time, then certain questions follow from it. It seems to me that these are chiefly two. One concerns the nature of science. The other, the nature of the world. What is to be the fate of science in an emergent world? We've been arguing in these lectures that science must necessarily be mechanistic if it is to be successful. And we've given the two main reasons for this. The rational principle of Occam's razor, or that the simpler explanation is always to be preferred, and the necessity of empirical prediction and experimental verification. It has long been assumed that to be mechanistic is also to be reductionist. But in an emergent world, science is no longer to be reductionist. Is it possible for science to be mechanistic without being reductionist? Perhaps not science, but the scientist. I am not asking for any changes to science, which within its own sphere has been fantastically successful. What is most necessary is that the person of the scientist should be able to recognise that there is more to the phenomenon of life than mechanism. My second question concerns the nature of the world. If the theory of emergence is correct, as we just saw, there is no single epistemologically privileged level of reality, as scientists previously assumed, but there are different levels. This ties in well with the account that we have been giving in these lectures of the phenomenon of life. For we have pointed out the immense difference between the living world and the inanimate one. And within the living world, we see that there are a number of levels of life, at least 4 by my reckoning: the archaea, or most primitive, plants, animals, and human beings. Just how these levels relate to one another from the viewpoint of explanation remains to be seen.